Okay, let's continue our lecture. All right. So we are going to starting from this equation. So the main reason for the we need to develop this equation further is that our question is we would like to obtain the velocity profile. Okay, velocity profile, the u. So to obtain the u, you need to do, absolutely, you need to do some the integration. Okay, so we can get these two constant over here. So determine these two constant value, the C1 and C2, we need to use the two, we need the two boundary condition for determining C1 and C2. So for the boundary condition, if you see this diagram, so first, we can assume, we can know that at the center part, at the axis part, because the upper part and bottom part is the exactly symmetry. So which means that in the velocity profile at this point, the gradient is a zero. Okay, the this part should be zero at the r equals zero. And the second one is this part at the wall, the r coordinate with this radius of this tube is that the velocity is a zero because of the no slip condition. By using these two conditions, we can determine the C1 and C2. So to determine, because we already know this is a zero, so we would like to use this equation, not using this one. So in that case, if you plug in all the value, in the case, you can determine the C1 equals zero. For the determine the C2, we can use this equation because the C1 part is a zero and the C1 part is zero, we can we can simplify this equation like this. And then we plug in, r equal large R, I mean this radius of this tube, and then you will get the C2 value as well, like this. So therefore, we did this one. We can plug in the C1, C2 value onto this original equation, and then we can conclude that the velocity profile looks like that. So basically, this is the pressure gradient on the x part, and this one x part is this axis, the axis direction, and then the other part is a geometry parameter. So let's further let's but the sorry so but the practically the pressure gradient also, it is not the this is also a random box, so we need to further develop this equation. So to determine this part, we are going to use this relationship, the continuity equation of the basic form. The volumetric flow rate is equal to the cross-section area times the velocity. So basically, you can make this equation, the average velocity times the area. In the case, you will get this equation, this relation, and then also this volumetric flow rate is we can make this equation, and then you can do some of the mathematics. In the case, this one also we can conclude this one. But the thing is, this value and this value should be identical, right? So we can put this upper part, the left hand side, put in this value, and the right hand side, put this part onto the right hand side. So in that case, you can determine the average velocity is like this. We can conclude that. So if you plug in this part, if we can simplify this part using the average velocity, because this term also have the dptx. So this one also have the dptx. So we can plug in all the value over here. In the case, you can get you can make this equation. So we can conclude that the average velocity, absolutely this part, and the velocity profile is looks like this. So base and maximum velocity at occur at the center part. So the maximum velocity is two times of the average velocity. And also if this part is zero, in the case this one is two average, right? But as you can see, this is the perfectly parabolic. So this relationship coming from this velocity profile. So let's talk about the practical one, the problem one. So let's solve this equation together. So our problem is that our geometry is the pipe diameter is a 20 millimeter. So basically the radius of the pipe tube is a 10 millimeter. So this is the half of the tube diameter is the radius, right? And also we assume that this length of the pipe is a 50 millimeter. And we assume that this pipe is filled with the air, okay? And we know the inlet velocity is 0.01 millimeter per second, okay? And density of the air, the material property of the density of the air is 1.225, and the viscosity of the air is this one. So because we know the order metric property and the geometry of this tube and also the average velocity, the inlet velocity, so we can determine the Reynolds number based on this equation. So we can get that this Reynolds number is a 13. So for around 14. So we know that based on those condition, that this flow should be laminar. So our question is, please solve this problem by using ANSYS Fluent. So we need to calculate the entrance length, and also we need to calculate the maximum velocity. Okay. So let's use the ANSYS workbench together. So this is the review slide again. So the simulation process basically from the design modeler and the meshing application and safety software. Okay. So design model, this is the geometric shape design, and meshing application. We need to generate some mesh and the grid, and also do some simulation. And here, this slide, I'm very detailedly describe how to click and how to use the ANSYS Fluent. So let's look at together. Okay. I'm going to follow this step. So I'm going to type the Fluent, not Fluent, sorry, workbench here like this. So and then here, as you can see, this is same the round workbench, and this part is the toolbox, and this one is a projection schematic, and this part is a property of the project schematic. The step two is that the analysis system, and here analysis system, and the fluid flow fluent, here fluid flow fluent, drag and drop like this, and then here you can see there is each element is generated, okay? And then step three, there is another way we can make this kind of the a module. So instead of the using analysis system, you can simply make geometry, mesh, and fluent. And here, let me see the safety post. Let me see. CFD post. Maybe result. Yeah, right. Over here. Okay. So, and then we link each of the module like this. Okay. So you can see the link transferred the data like this. Okay. Now this is the another. So basically this one is exactly same as this one. Okay. But here I'm not going to use this one. And I'm going to use this element. Okay. For the simply. So this is analyst system. You can read by yourself. And here also click the geometry. I think I don't need this one. So yeah, let's yeah, just look at this screen. And here, let me see. Just click here, the analyst type, the 3D, click to the 2D, change to the 2D, and then click the light mouse button. In the case, you can see, you can select and activate this screen. So you can select the new design model geometry. Case the design model will be pop up. Okay, like this. So let's go back. So we are finished this tab. So basically, this is the menu and toolbars and tree, so you can read by yourself. Okay, and then click this one, and change the unit. So here, the length of the unit meter. So I'm going to change to the millimeter. Okay. And the next step is to select the plane you want to sketch on. So we are going to use the XY plane, and then here look at face. In the case, this coordinate system is changed like this. And next step is the sketching mode. Using sketching mode, so there is a draw toolbox, modify dimension, constraint, and setting, etc. in here. And they click rectangular, make the rectangular like this. And then using the dimension over here, so using the horizontal tab, and then click this two part, and then just click in and movement down, and then just click in this side, and click the vertical, then just click like this. So this H1 and V1, we need to determine this value. So if you go back, let me see, what is the value? So here, the radius of pipe is a 10 millimeters, so V2 should be 10, right? And then this length is the H over here, the 50 millimeter. So here, the 50. Okay, so this is our geometry. And here, and also we need to use a concept as a surf in modeling concept. We can use this one like this, and the base object you need to you will see this one as a lightning box like this, and then click base object, and then select sketch one over here, then click apply. Okay, so here base object one sketch like this. And let's see, and then we generate it. So this one is generated, and as you can see, all the symbol is green, right? Which means it's a great, but which means it's a good, right? And so this is the finished, okay? So let's close. So the another way to use this ANSYS font, so instead of using this design modeler, you can use a space claim and other the discovery. So this is the new software, but the DM is the most famous one, I believe. But I believe you guys already know how to use the C a CAD program like SolidWorks or other CAD program is, I think this software is highly the compatibility of this ANSYS Fluent is quite good. So I think which any CAD software you can use it, and then just I will show some the example over here. So here, here I make another sample, and then if you click the right using the right mouse button, then here import geometry, right? So here I already made some. I already to there is some history. So if you click the browse, in that case you can import your geometry. Okay, so yeah, this tab you can use it. So if you click import geometry, you can see that this is already checked, right? But make sure, even though you import your geometry is absolutely 2D, but you need to change this analysis type as a 2D, right? If you use 3D, absolutely you don't need to change the analyst type, but if your case is a 2D, in that case, you need to change over here, okay? Okay, we delete this box, okay? And then next step, it should be same. So you can use a SolidWorks, okay? Okay, let's go to the mesh part. Just double click it. Okay. Mm. Ah, okay. So it shows something right here. Okay. So, alright. And okay, you can, yeah, this is general part. So here you can see there's a lightning button over here again, and then so you can see your geometry over here. So let's follow this PP slide together, and the select line, select here the select line, and the click leftward using left mouse button. Then the RMB here is a left mouse button, okay? And then insert, and click sizing, okay? Let's do same thing on the upper, bottom, and right hand side, okay? So in the case, you can see this tab is activated, right? And changed. So if you click this part, okay, let me, yeah. And if you click this part, you can change each property, okay? So etching one. So this is element size, but I'm prepared to use number of division, and then click 10 over here, okay? And this part, I'm going to, I forgot. Okay, this is 20. I'm going to put this part, so 20, okay? And this part, I'm going to put number of division, 20 as well. And this one, division 10, okay? And then next step, okay, let's do some, make a mistake. Okay, let's update it over here. So yeah, this is the result of the mesh generation. But our expectation is that this part and this part is smoothly linked, but this one is not good. Yeah. So to change this property is the click face over here, and then click again, click insert, and then let me see face meshing over here. And then if you see the lightning button come up again, and then and generate mesh. So this one is, but compared to the previous one, this one is good, but this one still looks a little bit weird, right? It's a little bit weird. So let's make this line is a little bit more uniform mesh, let's make a uniform mesh. So let's click this edge size again, and the, here the capture curvature is yes. You need to uh click the curvature is a no. Let's change everything. This one is no. This one also no. And this one also no. And further, I want to make this behavior is soft, but I want to do more strict rule where the behavior is hard. Okay, so to make a uniform mesh, the behavior hard is preferred. Okay, let's change this part. Okay, and then let's generate mesh. Let me check here. Yeah, this is the same. Okay, we got the uniform mesh. Okay, well, looks good. And then our next step is we need to mesh name selection. Okay, so click this etch button again. Okay, etch button again. Then click this part. Why I cannot click this one? Hmm, I cannot. Oh, okay. I don't know why I cannot click it. Oh, okay. I see. Okay, so here, if you drag like this, and you can select this bar and then click a right-hand side mouse button, and then see the create name selection over here. So this is what the let's make this one condition the velocity inlet. The velocity inlet. Let's do the same thing over here. This is the what here the var. Okay, var. This part is the axis, right? Let's see. Axis. This part is pressure outlet. Okay, so we select all of them, and then finally we need to okay, and let's click this part, the face, and then drag. And then this one is turned green, and then click the create name selection. This is a fluid. Let me see. This is I could fluid or oh, okay, fluid. Okay, with fluid. Okay, so you can see all the part is generated. A is the velocity inlet is correct. B is the wall correct. C is the axis correct. D is the pressure outlet correct. E, but this part is fluid. It's correct. Okay, and then last part is we need to save project, right? Before we do some, it is good idea to save each step. So usually after the mesh part, I usually do export to this file as a Fluent input file. Click export. You can just save it. Okay. Okay. So I will close it. And you will follow the step. You will know how to export those data. And then this is still lightning button, and then click update it. And then you will see this lightning button will turn in a green. Okay, so this is setup box. And then let's from here setup is the fluent. Okay, let's do the fluent together. here there's a lot of options, so it is recommended to use a double precision. And for the parallel, for the student version, I think maximum is the 4. But this case is very simple case. I'm going to not use the parallel server. Okay, and then just change this part and then click start it. Okay. It takes some time. So you can see that this console, so it says it's done, right? Which means it's good. Okay. 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 So this part, yeah, we call the outline. This part is task page, and this part is window, and this part is the command or the console part. Okay, in the outline part, as you can see, there is a lot of setup part. So this first section is setup. So basically, we select the mathematical model and the governing equation part, and also the what should I say? The choose the boundary condition and also the typing the boundary condition, the number like a velocity the velocity like a 0.01 meter per second for our case. And for the solution part, you can further, this is the mathematical part. So in this class, we are not going to too much detail look into the solution part. Okay, so, and also in the solution part, this and the monitor part, we can choose the convergence criteria as well. And also the for the numerical analysis, the initialization is absolutely is required. And also, and the last part is the long calculation part. And the last thing, and the result part, after the you do some the calculation, with the result part, you can make a fancy diagram in this section. So let's do at the first step here, because in the general, if you click the double click over here, see the general. So our case is basically axis symmetry, right? So click axis symmetry, and also the scale. Let's see. Our thing is that the length is the 50 millimeter is correct, and the radius is 10 millimeter is correct, right? So this one you can double check over here. And yeah, I think here we don't need to change. And usually I'm going to after finish the general tab, and then I usually go to the next step like this, and from up to the bottom, and then after click in the setup and go to the task page. Okay, so click the model. You can see the most there is a lots of the model over here, but here we only learn the viscous part. Okay, because the viscous part, this is the okay. Again, I want to highlight that the fluid, the fluid unique property is viscosity because of the viscosity. So this part we call the viscous part. Okay, if you click here, there's is a loss of the model over here. So basically, in viscid part, the viscosity governing equation of the viscosity part is not that important. If you click this one, in that case, your equation becomes the Euler's equation. The Euler's equation is which means that there is no viscosity term. But if you click the laminar, this is exactly the NS equation. So our case is the laminar. So I will click the laminar. And other part is the turbulent. There's a lot of the turbulent model, but we are not here. We don't have enough time to tell this each model. And so honestly, I also cannot tell you what is each model the characteristic. Okay, and this each model has a usually do some the validation and verification part. The we do the we choose the we do the simulation with the each different we choose the different turbulent model, and then after the after we get some result, we just compare this result with the experimental data, and then in one of the model is the close to the experimental data. In that case, we tell the people that this turbulent model is appropriate to use for this problem or this situation or this experiment or this system. Okay. Okay, so and then other things is the energy term is basically if you turn on the energy, in the case, we can conclude the temperature part as well. So, and the multi-phase part is basically this one is talking about is if there is a not only the gas and but also there is some liquid. In the case there is a two phase over there, so in that case we need to use the different model. So in the multi-phase model, if there is a more than the two phase, more than one phase, in the case we should use the multi-phase model as well for the Eulian precipitation. So if you do not use this multi-phase model, and then you need to simulate your model with the just turn off the multi-phase model. In that case, you need to calculate your model with the Eulian model plus with the Lagrangian model. There's another tab, but we are not going to talk about this part in here. And also there's a radiation. This is also related to heat transfer, and heat exchanger also related to heat transfer. And species model is basically if there is some chemical reaction is happen in the engine or uh, the engine or the other like chemical process. In the case, the species model is usually turned on, and the discrete phase model is this is uh, the Lagrangian model. Okay, so this is a very unique model. So this part also we are not talking about that part as well. And solidification and melting part. This is very you can straightforward understand. This one is there is some the phase is changed from the liquid to the solid or the solid to the liquid or liquid to the gas. In the case, this one is should be activated, and acoustic structure and other electrical property also there's this model also activate in the fluid. So yeah, and here our problem is very simple. So we are only going to use the laminate, okay, and the material tab. So here there is a fluid is air and aluminum, but the thing is there is no solid part, so you can just neglect this solid part. But the air part is quite important. So just double click this air. In the case, you can see that this property. So this is a default property, but I already said that this property is the same as our case. So I put the 1.225 over here, and the viscosity is 1.7 blah over here. So, and also here we can change you can use the ideal gas rule for calculate the density, or in compressible ideal gas. There's a lot of the equation form over here, but our case, we are going to assume that density is the constant. And the viscosity also same. So viscosity, if you use the viscosity also there is a loss of form. In the previous lecture and today's Libby lecture, I already told that for calculating viscosity, Sutherland formula is recommended. But the thing is, we are not going to use the energy equation, so we cannot use the Sutherland formula. So we are going to assume that this is the viscosity is the constant. But the okay, so we are going to assume that this one. So, and also in the using the Fluent database, you can change your fluid using, you can select those value over here. If you cannot find this fluid material in the database, in that case, you can uh, change the name like a something view. Then you can change the density like this. Okay. Okay, so this is the example. Let me double check. This is not changed. Okay, this is not changed. Okay. So this part is finished. A Celjo condition, there is an this part we are going to skip it. So there is nothing we can do for our situation. For the boundary condition is the most important part. So if you click the boundary condition, double click, and you can see in the task page there is a four type of the boundary. So axis is basically this yellow one, right? And interior fluid is this green part, is the inside of this tube. And the pressure outlet, this red one, and the velocity inlet, this blue one, this wall is this white one. Okay. So if you click axis, for the boundary condition of the axis, there is nothing we can change, right? And also in the type one, if you uh, make some mistake in your boundary condition, in the case, yeah, you can change in here as well. Okay. And also interior fluid, nothing we can do. Okay. The pressure outlet, we can change the pressure, the gauge pressure, but here our case, we are going to use the gauge pressure as a 0. Okay. The velocity inlet, we know the value of the value. So we're going to use type in the 0.01 over here. And also you can specify a specific, you can change the method, the magnitude and direction component. The component means that there is a velocity. So if you know the velocity, like x component is 3 and y component 2 meters per second and z is a 0, in that case, you can use this type. But usually in this case, the magnitude normative boundary, right? So we already know this is the perpendicular to the this line. So we are going to use this one. So most of cases, most of the engineer using this tab. Okay, at the select the 0.01. Fine. That's it. And where this is no slip condition, right? So this is stationary word. So this word is stationary. So this is same. And sure condition is no slip condition. Okay, this is also same. Okay. Okay. Here and other things is not that important. Okay, we're going to skip it. And last, going to the solution part. If you click the method, so in the previous, the Fluent version is most of the scheme is default value is the simple. But I don't know why in the latest version of the Fluent, the default value is coupled. But the coupled is I don't like the coupled method, so we're going to use a simple one over here. So this solution method is a little bit different by each method, but if you would like to know this part, click this question mark over here. So in the case, you can see the help part. So you can read this part. In the case you will know each scheme is which part is which one is different by which this I mean the scheme is simple method is different by the other method, something like that. So yeah, in this class we are going to use a simple and the control tab. Usually this value, we are going to use the default one, but in sometimes even though your mesh quality is good and other things good, but your this numerical your numerical procedure your numerical calculation is divergence or it is difficult to converge. In the case this relaxation factor you need to adjust slightly. Okay, for example, the pressure part, you can change the like a point 0.3 to the point 0.4. So most of the simple case, this solution control part is usually we don't change it. Okay, and the monitor part for if you click the ledger, so here the check convergence is already activated, but usually this one is unchecked, this check convergence. The other part is we can just skip it. And initialization, in your numerical method textbook or in the classical way, we usually use a standard initialization. So for example, we know the velocity inlet, right? So we can just put this velocity inlet like this and then do the initialization. This is the common, the classic way to initialize this condition. But the I don't know this algorithm, but this one is a quite good initialization method. So I usually use a hybrid initialization. So you can just click. This is the default one, and then here you can just click initialize. In the case, you can see the console box, you can see those value is appear. Okay, and then you will see the hybrid initialization is done. So likewise, the standard, if you want to use the standard, the classic way, in the case, you can type in your known value over here, and then initialization. Yes, yeah, it's done. Okay, so this part also completed. So let's run the 350 times. So just change those number and hit the calculation button. So because our case is extremely simple, so this calculation speed is very fast. So that and this is my computer is not that good, but you can see this calculation part is quite fast, and the calculation is completed. Uh, and then let's see the result over here. So velocity in, yeah, let's see the fancy one first. Click the graphics and the click backtrace, the double click, and then just use the default one and the velocity, the save. You can see, yeah, you can see this profile, right? But the thing is, I want to make an outline over here. In the case, click the draw mesh and then display, but I don't like to see the interior part. I want to see the face like this. In that case, just click it. You can see this profile like this. Okay, and then let me see the here. If you click the, because this is symmetry, right? Even though we only calculate in the 2D part, but we will, if you want to see the bottom part as well, in that case, click the view part, click views, and then mirror plane. This is axis. Click apply, so you can see the bottom part also appear. Yeah, appear. Okay, and then let's see which part we should also talk about in here. Okay, and here, if you click the vector, yeah, let's see this one, yeah, a little bit more detail. If you click the vector part, click save and display, the maximum value is automatically calculated. So this one is the maximum value is 0.0198, but our estimation based on the theoretical method, this our maximum value should be two times of the average velocity. So which means is that our the theoretical value is a 0.02, right? So let's go back to the our slide. So here, Okay, so hand calculation. Oh, sorry. So hand calculation for the entrance length. Yeah, let's see this part first. For the hand calculation part, so entrance length we can easily calculate by using this equation because we already know the Reynolds number. So this you can see our estimate value is around 14 millimeter, right? For the maximum velocity, based on this slide, okay, page 28, based on this slide, we know the maximum velocity is 2 times the average velocity. So we already know the average velocity is 0.01. So X we can in the according to the hand calculation, so this should be 0.02 millimeter per second. So unit should be not italic, sorry. Okay, so okay. Yeah. So, I want to say that the maximum our handicap calculation value is 0.02, but our result maximum value is 0.0198. It's quite similar, right? And yeah, and for determining the entrance length, so here we can also see that approximately, uh, it looks like here the entrance length, absolutely this part is not the fully developed, but this part is fully developed, right? According to this diagram. But we would like to more quantify this result, right? So if you click the plot, even though this is fancy, but it is difficult to quantify the result. So I want to make a more quantified result by using XY plot. So we can click the velocity over here, and then surface is the axis. Okay. So if you click over here, you can see that uh at the axis, which means at the center point, right? At the center point, it's at the beginning, because our elet is the 0.01 meter per second, right? So this is correct, but it is go up and go up. And then this part is looks like fully developed, right? So this value is around 1.98. So if you compare, so here is a detailed process. So if you make a guideline, yeah, you can use this step as well. So if you compare the result, is that the is error is around 1%. Okay, this is result is quite good. But this is only one verification. But we also would like to verify our result with the entrance length. So to determine entrance length, let's go back to our slides. So entrance length is this is the definition. Hydrodynamic entrance length is the where the wall shear stress reach within the about 2% of the fully developed value. Okay, wall shear stress is this one, right? So if we assume that the flow is fully developed at the x equals 0.05 meter, okay, our hand calculation value is a 14 millimeter. So 50 millimeter, we can assume that should be fully developed, right? So to use this definition, I make this equation. So here, so x at the fully developed laminar and the x equal fully developed region should be less than 2% error, right? But according to this wall shear stress, the definition, I can put those value like this, right? And then we can use this viscosity is the same term, so we can neglect, and then our finally we can get this relationship. So as you can see, the actual velocity, the derivative, we can just compare the actual velocity derivative, right? So here we can, in the xy plot, you can see the y function. Here, if we create the derivatives term, we can also like a d actual dy. So here, I don't like this part, but I don't the this y should be a radial direction, right? In our case, right? So click this one, and then click. We would like to see the word, right? Click the save. In the case, we got this graph, right? So we let me see. We got this graph, but we still need to calculate this value, even though we get this one. So we need to extract those value from the Fluent and then do some the data analysis by using the Excel or other software. But usually the data analysis for me is using Excel. So in the Excel, so using just simple this error equation and then do some calculation like this, and I found that this value at the around between 50 millimeter to 17.5 millimeter, the 2% is occurred, right? This is 3%, this is 1.8%. So in the to determine the exact value, I used this equation. Okay, so this is just a ratio. This is very easy. And our numerical entries length is around 70 millimeter. Error is quite big, right? So let's do these things together over here. So here, we already plot this the actual velocity divided by dr. Actually, y should be r, and then click the write to file, and then click write. And then this is lecture 03. Uh, uh, with students. Okay, like this. And then let's go to the here and see file. Oh, I don't know where I save it. Let me see. Double check. Hmm. All right. Let me sorry, I will make a file on the desktop test. Here there's a test file is uh sorry for the Korean, and using the notepad you can extract those value over here. So we can just simply copy it and paste on your Excel file like this. So this one is the X value, and this one should be the dr value, right? So I would like to compare those error term. So ABS, this one with the this should be reference value, sorry, and then divide by reference value. This ABS should be here. So, okay. Let me double check, sorry. This should be -7. Oh, it's correct. Okay. Hmm, interesting. Ah, why this is so different? It's -7.75. Oh God, sorry, I made big mistake. Yeah. Ah, God. All right, sorry. So this is error. Oh, sorry, I made some mistake. So let's see here. So they should be located over here, right? Between the 50 millimeter to 70.5 millimeter. Okay, the result should be located over here. So if you do some mathematics by using this formula, in the case you will determine this one is 7.1. Okay, 7.1. Okay, so if you compare the hand calculation, this error is quite big, right? So how to, so if we make a plot like this, right? So how to improve this error? So maybe in next lecture, we are going to discuss this part together. So this is the end of the today's class. So let's review. Okay, let's review. So summary of the today's lecture. So what is the internal pipe flow? So we flow, there is a two type, the internal flow and external flow. Especially for the pipe flow, this is driving force is pressure, and also this pipe. The reason why the pipe flow is so important is that, as you can see, there are so many application part. Okay, and understand the steady and the laminar flow in circular tube by driving the velocity profile and also calculating the entry length. I think it is quite good to practice and to review the fluid mechanics. And also we drive the velocity profile gradient by using the directly apply the Newton's second law, and also or we just make the assumption, several assumption, and then solve the Navier-Stokes equation. And also we run the how to use the ANSYS Fluent, okay, for simulating this 2D pipe flow. So this is assignment, okay. So I think you can do some the assignment by yourself. This is it. There's a three question over here. So if you answered this question on your the report, you will get the full report. Okay. Okay. This is the end of the today's lecture. Okay. Thank you for listening, and let's see the next lecture. Thank you.